All right, let's review this key theorem, and then I'll prove some of the conditions in the theorem. This is a theorem about cosets. So here we have H as a subgroup of a group G, and G1 and G2 are elements of G. So H is a subgroup or subset of G with closure properties, and these are two elements of G. So let's just draw a picture here. Let's do it up here. So here's G. G is the big group. H is a subgroup. And G1 and G2 are elements of G. Now, G1 and G2 both determine cosets. Let's suppose that G1H equals G2H. So that means there's a coset G1H would happen to be the same as G2H. Now, of course, G1 is contained in G1H, and G2 is contained in G2H. Why is that? Because G1H is G1 times every element of the subgroup H, and the subgroup H contains the identity. So G1H contains G1 times the identity, or G1. G2H also contains G2 times the identity, or G2. So I shouldn't have called this H. Let me erase that. So let's do it again. This here I would call, this is G1H, and it's equal to G2H. All right, so suppose I have a coset that contains both of these, and in fact the coset from G1 is equal to the coset from G2. Then you can conclude all these other things as equivalent conditions. G1 inverse G2 is in H, G2 is in G1H, G2H is contained in G1H, and HG1 inverse equals HG2 inverse. Right? So notice that 4 seems to be a weaker condition than 1, but as soon as you show one coset is contained in the other one, then in fact the two cosets are equal. So here's an example in a simple case. If we take G is equal to Z, and we take H equal to 4Z, we have, for example, that 3 plus 4Z equals 7 plus 4Z. You can list the elements of 3 plus 4Z and see they're the same elements as 7 plus 4Z. Now, this is the same thing as saying that minus 3 plus 7 is in 4Z. Okay? Why did I put minus 3? Because minus 3 is the inverse of 3. All right, so this G inverse 1 G2 corresponds to minus 3 plus 7. Remember, in this group here, in the group of integers, my group operation is plus, so I write plus instead of times. On the other hand, that's the same thing as saying that 7 is in 3 plus 4Z, which it is, because 7 equals 3 plus 4. Right? So these three conditions work together, are kind of compatible, and in fact are identical. And then you also have 7 plus 4Z is contained in 3 plus 4Z. In fact, they're the same coset, so the containing works as well. And then 4Z plus minus 3 equals 4Z plus minus 7, which is condition 5. All right, so in this video, I'm just going to do D. I'm going to show condition 4 implies condition 1. Okay. Now to show this, I only need to show that G1H is contained in G2H. Okay. Because I've shown G2H is contained in G1H, usually when we show two sets are equivalent, we show they're contained in each other. All right, and that's, I need to show given G1 is contained in G2H, given that G2H is contained in G1H. That's what I'm given. That's condition 4, and I'm going to use condition 4 to prove condition 1. Now to do this, I need to show that any element of G1H is also an element of G2H. That's how we show that one set is contained in another, that every element of the one set is contained in the other set. So let me go ahead and do that. I need to show any element of G1H is an element of G2H. All right, so what I need to do is take any element G1H of the coset G1 big H, and I need to show that this G1 little h is equal to G2 H double prime for some H double prime in H. That's the same thing as saying that G1 little h is in G2 big H, because every element of G2 big H can be expressed as G2 times some particular element of H. Okay, so that means I need to express G1H in terms of G2. All right, so let's go ahead and do that. Since G2H is contained in G1H, that was my hypothesis, it follows that G2 times the identity is in G1H. Okay. This implies that G2 equals G1H prime, where H prime is in H. Okay. Now I need to express G1H in terms of G2. This gives me a way to do it. If G2 equals G1H prime, then I can multiply both sides of this equation by H prime inverse, and that gets me, after one step, that gets me G2H prime inverse equals G1. Now I can substitute that in to G1H. G1H is equal to G2H prime inverse times H, and I can write that as G2 times an element of big H. So I'm going to let my H double prime be H prime inverse H, which is an element of big H, since big H is a subgroup. So G1H equals G2H double prime, so that means that G1H is in G2 big H, and this completes the proof that G2H is equal to G1H. All right? So if that's too fast for you, go back over it step by step, and you'll see that it works out. So I'll stop here on this video, and we'll take up the next part on the next video.